Alrighty, I hope you all are doing well today. For today's lecture, we are going to be talking about the various circuital laws that you guys got exposed to back in the Engineering 120 series, but we're going to go into a bit more detail about them today. So the first of the circuital laws that I want to talk about is Ohm's law. So way back in the 1840s, if I'm not mistaken, a physicist by the name of George Simon Ohm carried out a series of experiments. And I'm going to draw a simplified representation of what those experiments look like here. So let's say that we have a network of interest, and I'm going to represent that network by a black box where we don't really know what's inside of it. So this will be our, let's call it a device under test. Or DUT, like so. And this device was a two-terminal device. So I've got a terminal on top and a terminal on bottom, like so. And what Mr. Ohm did is he applied a source across the terminals of the device under test. Now, he chose to use a voltage source, but it could have just as easily been a current source. So I'm intentionally going to leave things ambiguous here and just put a circle, not saying specifically whether it is a voltage source or a current source. And what he did is he measured the voltage drop across those terminals, and he measured the current flowing into the network's terminals, like so. And he found that the current flowing through the network and the voltage across the network were proportional to each other. Okay. So he called the constant of proportionality between those two quantities, voltage and current, resistance. Okay. So from Ohm's experiment, we could say that Ohm's law tells us that our resistance R is equal to the ratio of the voltage drop across the terminals of a network of interest divided by the current flowing into the terminals of a network of interest. So let me just make a note right here. This R stands for resistance. And we can see, I think, pretty easily that the units of resistance are going to be 1 volt divided by 1 amp. Since voltage is measured in volts and current is measured in amps, and we commonly call this 1 ohm, where the symbol is capital omega, like so. Now, realistically, um, the reciprocal of this relationship, so current divided by voltage, is also going to be a constant of proportionality between these two quantities as well. So over here to the right, I'm going to do another version of Ohm's law that you guys probably aren't familiar with. I'm going to say that G, which stands for conductance, is equal to the ratio of current divided by voltage, which is the same thing as just the reciprocal of resistance. So this G, as I mentioned a moment ago, is conductance. It has units of amps per volt, which we commonly call a Siemen, Siemen, like the German electronics company, and its symbol is capital S. So these are two different representations of Ohm's law that we will see. The overwhelming majority of the time, we are going to use the R representation for resistance. There will be few and far instances in between where we use conductance in any of our circuit analysis until we get into some later courses. So for the intents and purposes of circuits 1, anytime you're given a conductance, just take the reciprocal of it and treat it like a resistance and go on about your day. There's really not a whole lot of point to learning the special rules and relationships that govern conductance in this particular class. So let's talk a little bit about what resistance actually does. Okay. So back in engineering 120, and this is the one that I can speak the most about because it's the one that I've actually taught in the last 5 years. You guys were asked to implement the following circuit. So I'm just going to kind of draw it right here. Looks something like this. So you had your 5-volt supply. Then you had a resistor. And if memory serves me correctly, this resistor was usually 220 ohms, but sometimes you put larger resistors in there. We'll talk about why that is in just a moment. And then connected in series to that resistor was an LED. Or I'm just going to make a quick note here that this is our light emitting diode or LED. So my question for you guys right now is, what was that resistor doing in that circuit where you guys first got exposed to electrical concepts? Anybody have any thoughts, or can anybody remember?
The LED would just light up, and depending on the resistance value, it'd be brighter or darker.
Okay, so Colin's 100% right. Depending on the size of the resistance, the intensity of the light got either brighter or darker. Um, Colin, just because you're obviously paying attention, do you happen to remember what would happen if you didn't include the resistor at all?
Your LED would be fried.
Exactly right. Your LED would burn out. So what the resistor was doing in this particular application is limiting the amount of current that can flow through the LED. Okay. So the internal resistance of an LED is usually pretty small. So if you put a full 5 volts across it, it would drive so much current through it that it would literally fry the internal semiconductor material, burning it out so that you could never use that LED again. The resistor was there to limit the amount of current that flowed through the LED. And the larger the resistor you put in series with the LED, the dimmer the light that was emitted by the LED became. So much so that if you put a 10 kilo ohm resistor there in series with your LED, which some students accidentally did, it was hard to tell whether or not the LED was even on because the light that it was emitting was so dim. So typically speaking, we used 220 ohm resistors or 470 ohm resistors for bright LEDs, somewhere in the ballpark of a 1K for relatively dim, and then anything larger than that, it was actually hard to see the light coming off of it at all. So we're going to use that kind of experimental results of figuring out what the resistor was doing to come up with some definitions for resistance. Okay. So I'm going to say that resistance is a measure of how difficult it is to pass current through a circuit element. So the higher the resistance value we have, the harder it is to pass current through that particular element. And then transversely, we're going to say that conductance is just the opposite of that. So conductance is going to be a measure of how easy it is to pass current through a circuit element. So I want to talk a little bit about how a resistor does its job, okay? And we're going to tie this back into some places where you see resistors used in your everyday lives. Whether or not you realize they were resistors is another thing. But so resistors are able to oppose the flow of current because they're made usually of what I would call an amorphous material, meaning like most metals are crystalline in nature. And so electricity flows pretty easily through metals because A, there's abundance of electrons, and B, the electrons tend to take a long time before they experience what I would call a scattering event. Okay. Whereas in an amorphous material that doesn't have a specific structure, electrons tend to bounce around and interact with the nuclei of atoms and things like that. So how a resistor actually impedes current flow is the electrons tend to, bounce around, and they're bouncing around and striking other electrons or nuclei or things like that tends to cause the material that the resistor is made of to heat up. Okay. So in essence, a resistor is just a device that's used to convert excess electrical energy into heat. Okay. That's all a resistor really does is it takes away some of the energy that we don't want to hit our LED and turns it into heat so that we can get it out of our system. Okay. Now, you guys have probably never thought about this, but that's exactly what like the heating element for an electric stovetop is doing. Okay. It is nothing more than a large, like physically large resistor. Okay. Um, we're going to talk in a moment about why it's got the shape it has and all of that kind of stuff as well. Same thing for the resistive element in a space heater or your dryer or something like that. Okay. It's literally just something that when you pass current through it, it tends to heat up, and then we use that heat for a specific application. Okay. So that's all resistance ever does is just convert electrical energy into heat energy. Um, for what it's worth, a resistor literally cannot store electrical energy at all. Any energy it gets, it winds up converting into heat. Okay. So I want to look at an equation for resistance that isn't Ohm's law, that relates resistance to two things. Okay. So the first thing is going to be the material properties of whatever the medium that the resistor is made of. And the second one is the geometry of the resistor. Okay. And so that relationship is as follows. We could say that resistance R is going to be equal to rho underscore E, where that is what's known as the electrical resistivity, and it is a material property. So I'm going to put a note here. multiplied by the cross-sectional area of the medium, divided by L, which is just the length of the medium. So pretty simple equation, resistivity times area divided by length. So the resistance of any particular object depends on what it's made of and how it's shaped, okay? And I want us to use this equation to confirm an assumption that we've been making anytime we've dealt with electrical circuits, okay? So back in engineering 120, 121, 122, etc., did you guys ever really pay attention to the length of the wires that you were using? Probably not, okay? They didn't really seem particularly important. And whenever we represented a wire on our schematic diagram, we just drew a line and we treated that line as if it were a short circuit, meaning that there's no voltage drop across it, okay? Well, in truth, wires do have some amount of finite resistance, but it's typically pretty small. So what I want us to do here is to calculate the resistance of a section of wire, okay? So as a quick example, let's say that we're going to calculate the resistance of a L is equal to 1 meter long section of AWG number 22 copper wire. Okay. So AWG number 22, AWG stands for American Wire Gauge, and 22 gauge wire is exactly what you guys were using in your engineering 120 classes. That's the type of wire that came with your kits, okay? Now, I don't expect you to know this off the top of your head by any stretch of the imagination, but the electrical resistivity of copper wire, rho E, is 1.68 times 10 to the minus 8 ohm meters at room temperature. And the diameter of AWG number 22 copper wire, at least according to Wikipedia, is 0.644 millimeters. Okay. So if we plug in all of the information that we were given, our resistivity, our diameter, which can be used to calculate the cross-sectional area, and the length of our wire, what we're going to find is that the resistance of a 1 meter long section of wire is actually quite small. So let's do that here really quickly, right? So we're going to have our wire is equal to 1.68 times 10 to the minus 8 ohm meters. Oh my goodness, I'm sorry. I actually have this backwards. This should be rho L over A. Let me swap those guys around. Sorry about that. That's what happens when I freestyle a lecture. There we go. Our length here is going to be 1 meter. And then down here on the bottom, and I apologize for my error again, we're going to have our cross-sectional area. So since we have the diameter, we're going to use pi over 4 times d squared. So that'll be pi over 4 times 0.644 millimeters squared. And then there are 1,000 millimeters per meter. And I need to square that conversion factor. So let me just double check things here. So I'm going to have millimeters squared over millimeters squared. So those guys cancel each other out. I'm going to have meters times meters. So that's going to be meters squared over this meters squared. And so all that's going to be left is something measured in ohms, which is indeed the unit of resistance. So when I throw this into my calculator, and I'm going to do that real quickly here, 1.68 times 10 to the minus 8 times 1 divided by, let's see, pi over 4 times 0.644 squared times 1 over 1,000 squared. So if I type this into my calculator correctly, and I believe I did just based on the number I got, I wound up getting a resistance of 0.05158 ohms. I'm going to call that approximately 50 milliohms. Okay. So we're dealing with something that's giving us a resistance in milliohms, which is obviously 1,000 times smaller than an ohm, or I'm doing 220 divided by that answer, 4,265 times smaller than the smallest resistor that we used back in the engineering 120 sequence of classes. Okay. So this is why we were able to neglect the resistance of our wires. Okay. This is the resistance of a 1 meter long section, where realistically, most of you guys probably only used, a few centimeters worth of wires for connecting all of your circuits together. Okay. So the resistance of a wire, as far as we are concerned in this class, is indeed going to be negligible, and we've just proven why. Okay. So I want to take this and I want to take another step from this realization, and I'm going to define a short circuit and an open circuit in terms of their resistance here. Okay. So a short circuit is just going to be represented by a straight line or a section of wire. Okay, so I'm doing some ellipses here to represent that this is part of some larger circuit. We've got our straight section of wire like so, and it is characterized by a resistance that is effectively 0 ohms. Okay, so according to Ohm's law, if we scroll up here really quickly, if we have a resistance of 0 ohms, that means that it doesn't matter how much current is flowing through it, because that's in our denominator. Our voltage must always be 0 volts, because 0 volts divided by any amount of current is going to give us a resistance of 0 ohms. Okay. So by definition, the voltage drop across any short circuit that we deal with in this class, we are going to treat it as 0 volts. Okay. Over here to the right, I'm going to detail an open circuit. And I'm going to put this in the context of it being part of some larger circuit as well. So an open circuit is really just any break in our wire or something like that. Okay. So in this particular case, we don't have a closed path that can carry current. So we would say that our current here, I, is going to be 0 amps. Okay. Because the current needs some sort of conductive path to flow through. Okay. Well, since I is in the denominator for our Ohm's law relationship, R is equal to V over I, we have something divided by 0. So that means that our resistance is effectively going to look like it's infinitely large. Okay. So we're going to treat any open circuit as an infinitely large resistance and any short circuit as an infinitely small or 0 resistance. Now, just for what it's worth, we know that real wires do have some resistance. Open circuits also have some amount of finite resistance. And you guys have probably experienced this in your everyday lives as well. How many of you, when you've been trying to plug something in or unplug something from an outlet, have ever seen sparks? Anybody ever
Yeah, I
seen?
have.
Yeah. So what's happening there is effectively um, the potential difference that's seen between the blades inside of the outlet and the blade of the plug, when they're separated, it gets so small that effectively we're able to break down that dielectric medium and cause current to flow across that open circuit. This usually only works when either the gap between the conductors is very, very small, or transversely, the voltage is very, very large, on the order of thousands and thousands of volts. So whenever we see sparks from an outlet where we know that our outlet is only providing us 120 volts RMS, it must be because our conductors are just really close together, but not quite completing that circuit. Okay. So just to recap here, short circuits have 0 voltage by definition and 0 resistance. Open circuits have 0 current by definition and infinite resistance. All right, so let me think about some things real quick. So we've talked about Ohm's law in terms of both resistance and conductance. I've given you definitions for each of those things. We've talked about how the resistance of a medium depends on both the material that it's made of and the geometry. We've gone a little bit into short circuits, a little bit into open circuits. So I'm going to wrap up this discussion on Ohm's law with just a few power relationships. Okay. So in our previous class meeting, we learned that power, P, was simply the product of voltage and current. And we can also say by rearranging our relationships that voltage, and this is just going to be Ohm's law as you guys are most familiar with it, is going to be equal to the product of resistance and current, which is the same thing as I is equal to V over R. And then in terms of conductance, we would have I is equal to V times G. And rearranging that guy, we would have V is equal to I over G. So we can take these relationships and manipulate them in order to get expressions for power only in terms of resistance and then one other quantity. So voltage or current, and then the same thing for conductance, and then only in terms of voltage or only in terms of current. So those relationships are going to look something like this. So in terms of resistance, we would have V squared over R is the same thing as I squared times R. And then in terms of conductance, we would have P is equal to I squared over G. is equal to V squared times G. Legitimately, I don't expect you guys to have to use those conductance relationships practically ever. I just want to make sure that I covered them just in case they do pop up in your web work because I didn't write those and it's been a minute since I've worked them. Okay. So before we move on from Ohm's law, does anybody have any questions? Okay, well, I just realized that I forgot to talk about the schematic symbol for a resistor and the schematic symbol for a conductor or conductance. So I want to do that really quickly. And then also I want to bring your attention to something. Okay. So this is one last little thing about resistance again. So our circuit diagram for resistance is going to look something like this, right? So there is our representation of a resistor that we might see on a schematic diagram. This is the representation of a conductance that we might see. And lo and behold, they're literally the exact same thing, okay? So the way that you're going to be able to tell the difference between a resistance and a conductance is by the units that are describing it, right? So here we should have R measured in ohms, and here we would have G measured in Siemens, okay? Now, another thing that I want to point out to you, and this is a little nuanced, okay? So let's say that the voltage drop across our resistor, I'm going to call it VR, like so, is positive polarity on the left, negative polarity on the right. And I'm going to say that the current that's flowing through our resistor, IR, like so, is flowing into the positive polarity terminal. So in this particular case, we find that V is equal to I times R, okay? Just the Ohm's law that you're familiar with. What if our current were flowing in the opposite direction? So what if the current flowed into the negative polarity terminal? Would we need to change Ohm's law in any way, shape, or form?
Just out of negative.
Exactly right. So anytime that we see our current flowing into the negative polarity terminal, Ohm's law needs to have a negative sign. And this is because resistors cannot supply power. All they can do is absorb power and convert electrical power into heat, okay? So this is one of the most common mistakes that I see students make, especially when they're starting out in this class, is forgetting that if current's flowing into the negative polarity terminal, Ohm's law needs a minus sign, okay? So I'm going to try to reinforce that a couple of different times today as we analyze some circuits a little bit later on. For what it's worth, doing the same thing here for our conductance, if this is VG and this is IG, then here we would find that I is equal to V times G. And if our current was flowing into the negative polarity terminal, we would once again have to put a negative sign on that Ohm's law relationship. Okay. All right. Let's move on from Ohm's law now and talk about Kirchhoff's voltage law. So you guys supposedly learned Kirchhoff's voltage law back in your Engineering 120 series, but I'm going to go ahead and spell it out from the beginning for you guys because it's been a moment since you've applied it. So Kirchhoff's voltage law, or more commonly KVL, states that the sum of the voltage drops around any closed path must equal to 0. So a couple of things that I want us to take away from this. Okay. So what I mean by a closed path with regards to Kirchhoff's voltage law is that if we start our KVL equation at one node and we end our KVL equation at that same node, we have formed a closed path. Okay. And I'll illustrate that here in a moment with an example. Okay. Another thing about this KVL relationship is that the polarities of the voltages are going to be incredibly important to us. So back in the 120 series, you had everything expressed as like a delta V kind of thing, and polarities weren't used. That has always particularly bothered me. So I'm going to be very, very explicit about the polarities and how we are going to apply KVL here. One third little tidbit, just for anybody who's interested or still paying attention to me ranting here. So we learned in our last class meeting that voltage is the work done per unit charge to move 1 coulomb of charge between 2 points in our circuit, okay? So KVL saying that the sum of the voltage drops, that's really related to the sum of the energy transferred as we push our charge around. So KVL is literally nothing more than the law of conservation of energy in circuits form, okay? It can never be violated. It doesn't matter what kind of circuit elements we have, if they're linear, nonlinear, whatever. KVL must always be true at all points in time, or we are breaking physics effectively, okay? So you can use KVL as kind of a sanity check to make sure that things are working out the way they're supposed to. Okay, so I'm going to give you guys, let's start with a relatively simple circuit. So let's say that I have an 8-volt source connected in series to some resistance R, like so, connected in series to a 4-volt source, which is in turn connected in series to a 7-volt source, like so. So what I'm going to find is the voltage drop across that resistor with positive polarity on the left and negative polarity on the right, okay? So how I like to follow or express my Kirchhoff's voltage law equations is I usually start at the bottom left-hand corner of my circuit or my path of interest. And then I usually go either clockwise or counterclockwise across all of those circuit elements, just adding the voltages together until I come back to the node that I started from, okay? So I'm going to work this the first time by going in this direction. So that would be clockwise around the circuit. So I'm just going to put a little note here. and say that this is number one. And then I'm going to redo it going the opposite direction, which I'm going to call this number two. And we're going to find that regardless of which direction we go, we're going to wind up getting the same result. Okay. So let's do this up here. Let's call this KVL number one. Okay. So I'm going clockwise around my circuit. So how I write my KVL equations is if I see the negative polarity terminal first, the voltage gets a negative sign. And if I see the positive polarity terminal first, the voltage gets a positive sign. So as I'm going up and I see that 8-volt source, the first thing I see is the negative polarity terminal. So that's going to look like negative 8 volts. Next, I see my resistor, and I see the positive polarity terminal first, so that's going to be plus VR. Then I see my 4-volt source. I see the positive polarity terminal first, so that's going to look like plus 4 volts. Then I see the 7-volt source. Again, I see the positive polarity terminal first, so that's going to look like plus 7 volts. And now I'm back at that bottom node, so I've closed my path. So I'll set this equal to 0, and then rearranging, I would find that VR is going to be equal to 8 volts minus 4 volts minus 7 volts is negative 3 volts. Okay. So before I redo this going the opposite direction, does anybody have any questions or comments about where any of those signs came from or anything like that? All right. So now let's go in the other direction. So going counterclockwise, the first thing that I see is the negative polarity terminal of the 7-volt source. So I would have negative 7 volts. Then I see the negative polarity terminal of the 4-volt source, so minus 4 volts. Then the negative polarity terminal of our resistor voltage drop, VR. And then lastly, I see the 8-volt source, and I see the positive polarity terminal first. So I set this equal to 0, and then I'm just going to rearrange, right? So I'm just going to move that VR over to the other side. So I would have negative 7 volts minus 4 volts plus 8 volts is equal to VR. And so from that, negative 7 minus 4 is negative 11, plus 8 is negative 3 volts. And exactly as I expected, I got the exact same result as I did earlier. So it literally doesn't matter which direction you choose. So just pick a direction that makes the most sense to you, and then just be consistent about it. Anytime you see the negative polarity terminal first, the voltage should get a minus sign. Anytime you see the positive polarity terminal first, the voltage should get a positive sign. Okay. So that is the basics of Kirchhoff's voltage law. Okay. And on its own, it's actually rather boring. So what we can do is we can use Kirchhoff's voltage law in combination with Ohm's law to do some more interesting things, okay? So I'm going to work another example with you guys, and it's going to seem like I have increased the difficulty level by a lot. And I'm not going to lie and say that I haven't, but with proper application of KVL and proper application of Ohm's law, we can actually find out a lot of information about this circuit pretty quickly. Okay. So this is going to be our second example. So here's the circuit that we're going to analyze. Like I said, it's going to be a bit more complicated. Here we have a 13-volt source. We've got a 15 ohm resistor, a 7 ohm resistor, this is a 9-volt source. Then down here on the bottom, we're going to have a 12 ohm resistor. This is going to be a current controlled voltage source. So plus minus, let's call this 8 IX, like so. And then over here is going to be a 13 ohm resistor. I'm going to define the current IX. Let me do it in maybe blue. So this is the current IX. I'm also going to define a voltage here, Vy. And what I want us to find is the value of the current IX, the value of the voltage Vy, and then the power, let's say, absorbed by the current controlled voltage source. Okay. So those are the 3 pieces of information that I'm interested in. So for this particular problem, we aren't given the polarity of the voltage drops across anything except our sources, which means we need to make a guess as to what the polarity across each one of our resistors is. Okay. So I am intentionally just going to kind of mix things up here. Okay. So let's say that the voltage drop across our 15 ohm resistor, which I'm going to call V15, has positive polarity on the left and negative polarity on the right. And the voltage drop across our 7 ohm resistor will be positive polarity on the left, negative on the right. The voltage drop across our 12 ohm resistor will be positive on the left, negative on the right. And lastly, the voltage drop across our 13 ohm resistor will be positive on the left, negative on the right, like so. Okay. So somebody who's paying attention, tell me clockwise or counterclockwise. Either say it on Zoom or type it into chat, whatever floats your boat.
Clockwise.
Clockwise. Okay. So I'm just going to make a note here that I'm starting down here and I'm going up. So if I write my KVL equation, the first thing that I see is the negative polarity terminal of the 13-volt source. So I'm going to have negative 13 volts. The next thing I see is the positive polarity terminal of that voltage V15. The next thing I see is the positive polarity terminal of that voltage V7. Then I see the negative polarity terminal for the 9-volt source. Then the negative polarity terminal for voltage V13. The negative polarity terminal for the 8IX voltage source, and the negative polarity terminal for the voltage V12, like so. And now I'm back to where I started from. So this is what my KVL equation looks like. So I have 1, 2, 3, 4, 5 unknowns and only one equation. So where the rest of my equations are actually going to come from is Ohm's law. Okay. So this is an example of a single loop circuit where all of my circuit elements are connected in series, which means they all have the same current flowing through them. Okay. So I should be able to use Ohm's law to express all of those resistor voltage drops in terms of that common current IX and take this five unknown, or one equation, five unknown system down into a one equation, one unknown thing just using substitutions. So below here, actually, let me give myself more room. We're going to deal with the Ohm's law stuff. Okay. So I'd like you guys' help, if possible, in using Ohm's law to express all of these resistor voltages in terms of that current IX. So let's start with that voltage V15. Would anyone care to venture a guess as to how we would express that voltage in terms of that current IX?
IX times 15.
So 15 ohms times IX. So I believe that Colin is correct. Okay. So the reason why I'm saying he's correct is because we know that Ohm's law is V is equal to I times R, or how I did it, R times I. And IX is going to be flowing into the positive polarity terminal of that 15 ohm resistor as it flows around its clockwise path. Okay. So similarly, we should be able to say that V7 would just be 7 ohms times IX, because again, our current IX is flowing into the positive polarity terminal. When we get to those other two resistors, though, our current IX is going to be flowing into the negative polarity terminal. So what we would find is that V12 should be negative 12 ohms times IX. And similarly, V13 should be negative 13 ohms times IX. So just so that we're all catching what I'm throwing here, this is our current IX as it's making its way around. So it sees the positive polarity terminal first. This guy already obviously sees the positive polarity terminal first. When we come around this way, following that clockwise path the current is taking, now it's seeing the negative polarity terminal first, which is why our Ohm's law got a minus sign. And again, down here, it's seeing the negative polarity terminal first, which is why V12 gets a minus sign as well. So just to, I don't know, beat you guys over the head with it, anytime we're applying Ohm's law, when the current enters the negative polarity terminal, Ohm's law should get a minus sign. So now we can substitute all of that stuff back in, right? So I'm just going to do this straight up here. So I'm going to have negative 13 volts plus V15 is just 15 ohms times IX plus V7. So that's just 7 ohms times IX minus 9 volts minus V13. So that's going to be a minus 13 ohms IX minus 8 IX minus V12, where V12 is negative 12 ohms IX. And this is equal to 0. And now we're going to simplify things, right? So I'm going to leave all of those IX terms on the left-hand side of the equal sign. So just for what it's worth, if I have a minus here and a minus here, they cancel out to make that guy a plus. If I have a minus here and a minus here, they cancel out to make that guy a plus. So I wind up having a grand total of, let's see, 15 plus 7 is 22, plus 13 is 35, minus 8 is 27, plus 12 is 39. So that's going to look like 39 ohms times IX. For those of you that are concerned that I lumped that 8 in there as if it were a resistor, remember that this is a current controlled voltage source, so the units on that scaling coefficient is actually 8 volts per amp, where a volt per amp is the same thing as an ohm. So it's perfectly acceptable that I just treat that 8 as if it were 8 ohms. Moving to the other side of the equal sign, I'm going to wind up, let's see, I have a 13 and a 9, so 13 plus 9 is 22 volts. And so from this, I could say that IX is just going to be 22 volts over 39 ohms, where a volt per an ohm is an amp. So if I did my mental math here correctly, and if I didn't, somebody please tell me, we wound up finding out that IX is equal to 22 over 39 amperes. Let me just throw this in a calculator real quick to make sure I didn't make some sort of dumb mathematical mistake. It is indeed 39, and then 13 plus 9 is indeed 22. Okay, and I algebraed it correctly by moving it around. Okay, so we figured out IX. Does anybody have any thoughts on how we might figure out that voltage VY? So conceptually, this is something that I've seen students struggle with a little bit. So we learned in our last class meeting that voltage is nothing more than the potential difference between 2 points in a circuit, where in this case, it's just going to be between 2 different nodes. So let me use some different colors here. So we're just finding the difference between this node up here, where the positive polarity terminal of that voltage VY is associated with, and this node down here, where the negative polarity terminal of VY is associated with. Okay. So I can write a Kirchhoff's voltage law equation in order to determine this thing. Okay. So what I'm going to do is I'm going to do KVL around, let me do it in maybe this light blue color so we can see it. Okay. So I'm going to go, just for the sake of argument, up across here, then to the right, then down, and then to the left, like so. And I'm just going to add those voltages together and then solve for Vy. It literally doesn't matter a lick that there is no current flowing down between that orange node and that purple node across that open circuit. Doesn't matter at all, because Kirchhoff's voltage law just says that the sum of the voltage drops around any closed path has to be equal 0. And we know that voltage is just the difference in potential between 2 points. So it doesn't matter if those points are connected to each other or not. Okay. So I'm going to do just KVL at blue. And that would look like negative 13 volts plus V15 plus Vy minus V12. is equal to 0. And now I'm just going to substitute in those Ohm's law relationships that we already have. So that would look like, actually, let me rearrange it a smidge. Okay. So I'm going to leave Vy on the left-hand side of the negative sign, or the equal sign. So there's my Vy. I'm going to move the 13 volts over. I'm going to move that V15 over. I'm going to move that V12 over. And now I'm going to substitute in. Okay. So that's going to be 13 volts minus V15. So that is 15 ohms times Ix, where Ix is 22 over 39 amps, plus V12, where V12 is minus 12 ohms times Ix. Ix is 22 over 39 amps, like so. And then I'm just going to throw that into my calculator. Okay. So 13 minus 15 times 22 over 39 minus 12 times 22 over 39. I wind up getting that Vy is negative 29 over 13 volts, if I type that into my calculator correctly, which I believe I did. Okay. So before I move on and we determine our power absorbed by our current controlled voltage source, does anybody have any questions about how I applied KVL around that light blue path, or where any of these numbers or signs came from? All right.
So can you go up
Sure.
to the picture? Yeah. I assume the orange node goes all the way to the 7.
Yes.
Okay.
Yeah, so
And
I could definitely extend that all the way over to the 7. In fact, I don't really know why I didn't do it other than I was just associating it with that positive thing there. But yes, it does technically extend all the way to the right.
so if I were to do instead of KVL to the left of the VY, if I do it to the right, would I stop at the where the orange ends, or would I go past it to where the 9 volts is?
So if you were going to do KVL, let me make sure I'm understanding your question correctly. I'll do it in this light purple color. So I'm going to choose to do a clockwise path just because that's what my preference is. So I would start at the purple node and go up like so, across, down, and then to the left.
All right, that answered my question.
Yeah. And it doesn't particularly matter which of those two paths I choose to write a KVL equation for, since they both involve Vy, I'll wind up getting the exact same result either way. The path in light blue is a little less complicated, which is why I chose to do it, but the one in purple isn't that much more difficult.
So if Vy is on the right side of the 8Ix, you would include 8Ix in your KVL?
So if Vy were moved elsewhere or where it's currently
Yes,
at?
sir. Like on the right side of the current control voltage source.
Yeah, so if, let me erase this stuff here really quickly. So if this Vy were over here, then my original KVL thing would need to extend over to there. Did that answer your question, Trevor?
Yes, sir.
Yeah.
Thank you.
Yep. All right, I'm going to put it back so that when I post these notes, the equations will make sense. Shit. Okay, any other questions before we move? Oh, actually, we still need to do that power calculation. Okay, so does anybody have any thoughts on how we might calculate the power absorbed by that current controlled voltage source? Actually, West Navar asked a question in chat. Let me look at this real quick. Is the V12 supposed to be positive or negative in the final Vy equation? So let's go down here and look at that, right? So let me make very obvious what I'm doing here, right? So I kept Vy on the left-hand side of the equal sign. So I moved this 13 volts over. I moved this V15 over. And I moved this V12 over like so. So when I'm moving them over to the other side of the equal sign, I should be changing the sign on each of them. So I originally had -13, here I have +13, so that checks out. I originally had plus V15, here I have minus V15, so that checks out. And then lastly, I had minus V12, so now I have plus V12. So all of that checks out. Now, another place where this might have got a little bit confusing is I have a plus sign right here and a minus sign right here. The reason for that is because I'm adding -12ix. So plus -12ix looks the same as just -12ix. Did that explain things, West? Great. All right, power calculation. Anybody have any thoughts?
So do you have to pick a direction and add up all of the voltage and current values to get the power?
So, I think you could do that, but that's probably not the most efficient use of our time.
Right.
So let me ask you a question, Alex. What's the voltage drop across that dependent source? You don't have to give me a number. You can just tell me what it is, I guess, symbolically, if you so chose.
Which dependent source?
There's only one dependent source. It's the 8ix source.
Oh, right. So it would be uh IX times that 13 ohms.
Well, so this is a current controlled voltage source. So I want the voltage drop across it. It's just 8ix. So our voltage would be 8 volts per amp times Ix, which is 22 over 39 amps. So that is our voltage. Okay. Are you okay with that?
Yes, sir.
What's the current flowing through our dependent source?
Is that just IX?
It is indeed just Ix. Is the current flowing into the positive polarity terminal or into the negative polarity terminal of our voltage source?
The negative terminal.
And we were trying to find absorbed power, so we just need to put a minus sign out in front. And now we can throw that into our calculator and get our power. Which we could have gotten it by calculating all of the other powers, and then whatever's left over was that guy, but that's a lot more work than V times I, and then just make sure that if the current's flowing into the negative polarity terminal and we're finding absorbed power, add an extra negative sign. So let me throw this into my calculator real quick. So 8 times 22 over 39 squared comes out to be 2 point, excuse me, forgot the negative sign, negative 2.546 watts. Does anybody have any questions about that power calculations, or did I explain it well enough from the jump? It's perfectly fine if you need further explanation. Alrighty. So now let's talk about Kirchhoff's current law. So there are really 3 different ways that we can think about Kirchhoff's current law, or KCL. So before I kind of write things down, I'm going to start with a picture. Okay. So imagine here towards the center of the page that we have a node point. Okay. And there are multiple paths that are connected to this node point. And all of these are part of some larger circuit. Okay. So I'm just going to arbitrarily make up some directions that currents might be flowing here. Okay. So I'm going to call this guy right here I1, and it's flowing into that central node. This guy is going to be I2, and it's also flowing into that central node. I'm going to define my current I3 as flowing out of that central node. I4 is going to be flowing into that central node, and I5 is going to be flowing out of that central node, like so. So our first definition for KCL is going to be the one that you guys learned back in the Engineering 120 series, and that is the sum of the currents flowing into a node must equal the sum of the currents flowing out of the same node. So for this particular system, I'm going to put the currents that are flowing in on the left-hand side of the equal sign and the currents that are flowing out on the right-hand side. So I'm just going to make a note here, in, and over here will be out. Okay. So I1 is flowing in, so it'll go on the left-hand side. I2 is flowing in, so it'll go on the left-hand side. I3 is flowing out, so it'll go on the right-hand side. I4 is flowing in, so it goes on the left-hand side. And lastly, I5 is flowing out, so it goes on the right-hand side. So this is how we would apply that particular formulation of Kirchhoff's current law to this system. Okay. So before we move on to our second option of how to express KCL, does anybody have any questions about this guy? All right. So Our second method for applying KCL is to say that the sum of the currents entering a node must equal to 0. So this isn't saying I1 plus I2 plus I4 is equal to 0, because we have to take all of our currents into account, okay? So if I3 is flowing out, then negative I3 is flowing in or entering that node, okay? So essentially, all of the currents that are already flowing in will get a plus sign, and the currents that are flowing out will get a minus sign. So we'll wind up having I1 plus I2 minus I3 plus I4 minus I5 is equal to 0. So mathematically, that's the exact same equation that we got from formulation number 1 for KCL, except that we moved that I3 and I5 over from the right-hand side of the equal sign to the left-hand side of the equal sign, okay? So we get the exact same relationship, it just looks slightly different. Our last formulation for KCL is just the opposite, okay? So it will say the sum of the currents exiting a node or leaving a node must equal to 0. And in this case, all of the currents that are leaving will get a plus sign, and all of the currents that are entering will get a minus sign. So that would look like negative I1 minus I2 plus I3 minus I4 plus I5 is equal to 0, which is the exact same thing as our relationship from formulation number 2, except that everything is multiplied by a factor of -1. And that should hopefully make sense to us, because we know that in order to change the direction on our currents, we simply multiply it by a factor of -1. So before we get into some examples here, does anybody have any questions or concerns about KCL? So one thing that I want to point out to you all is that you're welcome to use any of these formulations. Whichever one makes the most sense to you is the one that you should probably be using. And in some problems, just for simplicity's sake or making the analysis easier, I might use multiple different formulations of KCL. So at one node, I might say that, oh, I'm going to use formulation number 2, and at a different node, I might use formulation number 1. It just takes practice and consistency in order to get good with all of them. For what it's worth, formulation number 3 is the one that I use personally the most often, and it's because it's the one when we learn nodal analysis next week. Formulation number 3 will give us the least number of extra negative signs to deal with. And I know that I'm particularly bad at the bookkeeping side of things and remembering to include negative signs and stuff like that. So I prefer number 3 personally, but I still use the others as well. For what it's worth, since Kirchhoff's current law involves adding currents together, and we know that current is simply the rate at which charge passes any given point in a circuit, Kirchhoff's current law is really just the law of conservation of charge as applied to circuits. So essentially, if we added all of the currents together and they didn't make zero, then that essentially means that charge is either being created or destroyed at that node point, which we know can't happen, okay? So KCL and KVL are just the law of conservation of charge and the law of conservation of energy applied to circuits, okay? So this is another one where it must always be satisfied at all points in time for every circuit. Okay, so let's look at a problem. Excuse me. And I'm going to go ahead and jump to a slightly more difficult example, because I feel like the explanation itself kind of taught you the ropes here, okay? So let's say that we have the following circuit. So here I have a 6 kilo ohm resistor. This is a 6 milliamp source. This is going to be a 4ix current source. Here is a 2 kilo ohm resistor. Here's a 2 milliamp source. And lastly, I'm going to put a 3 kilo ohm resistor on the right-hand side of the page. And now I'm going to define a few things that we're interested in. So let's say that this voltage right here is going to be Vx. This current right here is going to be Iy. And lastly, this current over here is going to be Iz. And I want us to simply solve for Vx, Iy, and Iz. And we're going to do this using a combination of Kirchhoff's current law and Ohm's law. Okay. So in order for us to apply Kirchhoff's current law, we need to decide on which version of KCL we are going to use. And we also need to decide on which node we are going to apply it at, okay? So this is an example of what's called a single node pair circuit. That just means that everything is connected in parallel. So we really only have two options for node. It's either going to be the top node or the bottom node. So somebody just arbitrarily tell me top node or bottom node.
Top.
Top node. Okay, thank you, Joseph. Somebody else tell me if we're going to do KCL version 1, 2, or 3 at the top node.
2.
Number 2. Okay. So I'm just going to make a note here that we're doing KCL number 2 at the top node. So this is saying currents flowing into the top node are going to get a plus sign, and currents flowing out of the top node are going to get a minus sign. Okay. So we're going to work our way from left to right here. Okay. So is that current IY flowing into the top node or out of the top node?
In.
In. So it's going to get a plus sign. So we're going to have IY. Is the 6 milliamp current source flowing into the top node or out of the top node?
Out.
So I think it's
Sorry.
flowing. Yeah, so
It's
it's
in.
flowing in as well. What about the 4IX dependent current? Is that flowing in or out?
Oh,
Out. So it's going to get a minus sign. Now we have the 2 kilo ohm resistor, and there is no indication as to which direction the current is flowing. So we get to make a choice here. So somebody choose whether the current flowing through the 2 kilo ohm resistor is flowing up or down.
down.
Down. Okay. So I'm going to call this current right here I2K. And because it's flowing out of the top node, it's going to get a minus sign. So here's I2K like so. What about the 2 milliamp source? Is it flowing into or out of the top node?
Oh,
Out. So it'll be minus 2 milliamps. And then lastly, that current IZ, is it flowing in or out of the top node?
it's flowing out.
Also flowing out. Okay. All right, so we have one equation, and let's see, 1, 2, 3, 3 unknown quantities, right? IX. Oh, actually, sorry. IX doesn't exist, so this should be IY. That's my mistake. My apologies there. Okay, so I2K, and IZ are our 3 unknown quantities, okay? So when everything is in parallel like we have here, the best piece of information that we could find would be the value of the voltage, Vx. Because as we learned in Engineering 120, and as we can prove using Kirchhoff's voltage law, whenever we have things that are connected in parallel, they all have to have the same voltage drop across them, okay? So since everything in this circuit is connected in parallel, everything in this circuit has a voltage drop of Vx across it, positive polarity on top, negative polarity on bottom. So I believe that we can express all of those currents in terms of that voltage Vx using Ohm's law. So that's going to be my next step. And I'm going to give myself some room. So I'm going to start with that current IY on the left. Okay. So would one of you be able to help me express that current IY in terms of that voltage Vx?
EX over 6 kilo ohms.
So Vx over 6 kilo ohms. Okay. So you're very close. You've manipulated Ohm's law correctly, but I would argue that the current is flowing into the negative polarity terminal of the 6 kilo ohm resistor because the negative polarity terminal is on bottom, right? So essentially, IY, dang it, it's supposed to be blue. Starts down here, flows into the negative polarity terminal, and then flows out the positive polarity terminal. So whenever our current is flowing into the negative polarity terminal, Ohm's law needs a minus sign, and so I'm just going to add the minus sign here. Does that make sense to you guys?
Yes.
Alrighty. So for the next one that we see, that would be I2K, right? So just to make it a little bit easier on you, I'm going to explicitly write down. So because everything is in parallel, again, they're all going to have the same voltage drop across them. So all I need to do is just make sure that I put the polarity on the right side. So if positive polarity was on top over here on the left, positive polarity needs to be on top over here in the middle. And for what it's worth, positive polarity needs to be on top over here on the right as well. I don't know why I wrote Y instead of X, so sorry about that. So how are we going to express that current I2K in terms of Vx?
Should it not just be Vx over 2 kilo ohms?
Yeah, Vx over 2 kilo ohms, absolutely right. And because the current is flowing into the positive polarity terminal, we don't have to change the sign on Ohm's law, okay? Very similarly, we would see that IZ is equal to Vx over 3 kilo ohms, okay? And so now we could simply substitute these relationships in. So here where I see IY, I'm just going to replace that with minus Vx over 6 kilo ohms plus 6 milliamps minus, now I've got 4 IY. So that is a current controlled current source. So the 4 is a dimensionless quantity. So I'm just going to do negative 4 Vx over 6 kilo ohms, like so. So that's 4 IY. Then I have minus I2K. So that'll be minus,
Why is there a negative inside the bracket there?
because IY is also negative.
Oh yeah, I'm sorry.
No, not a problem at all. That's the signs are going to be one of the most difficult things to keep track of. So anytime it doesn't make sense, please ask, because there is a very much non-zero possibility that I have made a mistake. So never hesitate to ask me a question. Okay. So let's see. So then we have Vx over 2 kilo ohms minus 2 milliamps, and now we have minus Iz, which is Vx over 3 kilo ohms, is equal to 0. And so what I'm going to do now is I'm just going to move the constant terms to the other side. So let me think about this just really quickly for simplicity's sake. So let's see here. This minus sign and this minus sign cancel each other out. So I have 4 Vx over 6 kilo ohms minus Vx over 6 kilo ohms, I believe looks like 3 Vx over 6 kilo ohms minus Vx over 2 kilo ohms minus Vx over 3 kilo ohms is going to be equal to 2 milliamps minus 6 milliamps, right? And I'm going to throw this into the numerical solver on my calculator and solve for that voltage Vx. So give me just a moment to enter that. So let's see, 3x over 6,000 minus x over 2,000 minus x over 3,000 is equal to negative 0.004. So when I solved this in my calculator, I got Vx to be equal to 12 volts. Now that I know what Vx is, I can just plug that value in to find Iy, right? So negative 12 volts over 6 kiloohms should just be, so let me write this, negative 12 volts over 6 kiloohms is just going to be negative 2 milliamps. And IZ is just going to be positive 12 volts over 3 kiloohms is going to look like positive 4 milliamps. Okay. Does anybody have any questions or concerns about this example problem? All right, well, you have 10 minutes of class remaining, so you can, choose to use that time to work on the ICA and ask any questions that you may have of me, or you can, duck out a little early and enjoy the rest of your afternoon. Thank you guys so much for your attention. I'll see you on Wednesday where we'll talk about resistor combination techniques.